We now consider the real space, represented by R3, which contains the ordered pairs x1, x2, x3, where x1, x2, and x3 are all real numbers. Every element of R3 is a point in space, but it can also be regarded as a vector, pointing from the origin O towards that point. There are analogous notions of length, addition, scalar multiplication, dot product or scalar product for vectors in R3. The length of a vector x equals the square root of x1 squared plus x2 squared plus x3 squared. The addition of two vectors x1, x2, x3 and y1, y2, y3 equals the vector x1 plus y1, x2 plus y2, x3 plus y3. For any real numbers k times the vector x1, x2, x3 equals the vector k times x1, k times x2, k times x3. The dot product of two vectors x1, x2, x3 and y1, y2, y3 equals x1 times y1 plus x2 times y2 plus x3 times y3. All properties of these notions in R2 also hold in R3. Now let's talk about planes. First, let's define a normal vector on a plane. A non-zero vector n is called a normal vector to a plane if it is perpendicular to every vector on the plane. Note that if n is a normal vector to a plane P, then n is a normal vector to all planes parallel to P. Second, there is a unique plane with normal vector n passing through a given point A. To define a plane, it is useful to find its equation. Let A be a point on a plane with normal vector n. For a point x to lie on the plane, we require the vector x minus a to be perpendicular to n. In other words, n dot bracket x minus a equals 0. Let's label this as 1. If we let c equals n dot a, which is a real number, then the equation becomes n dot x equals c, which we call the second equation. We can use the components of the vectors to rewrite the equation as n1 x1 plus n2 x2 plus n3 x3 equals c, which is the third equation. These three equations are different forms of the equation of a plane. Let's look at an example. Suppose we want to find the equation of the x1, x2 plane. A point on the plane is A, which equals the vector 1, 1, 0. A normal vector is n, which equals 0, 0, 1. So the equation is n dot bracket x minus a equals 0. That is 0, 0, 1 dot bracket x1, x2, x3 minus 1, 1, 0 equals 0. We can further simplify the left-hand side to be 0, 0, 1 dot x1 minus 1, x2 minus 1, x3. The dot product simplifies to x3, so the equation of the x1, x2 plane is simply x3 equals 0. Let's look at a second example. Suppose we want to find the equation of the plane with normal vector n equals 4, negative 5, 2, and passing through the point A equals 2, 3, negative 1. Applying the definition, the equation is n dot bracket x minus a equals 0. By plugging in the vectors, we have 4, negative 5, 2, dot bracket x1, x2, x3 minus 2, 3, negative 1 equals 0. So we have 4, negative 5, 2, dot x1 minus 2, x2 minus 3, x3 plus 1 equals 0. By using the definition of the dot product, this gives 4 times bracket x1 minus 2 minus 5 times bracket x2 minus 3 plus 2 times bracket x3 plus 1 equals 0. This simplifies to 4 times x1 minus 5 times x2 plus 2 times x3 plus 9 equals 0.